Hi all. Today we will explore the fascinating world of kinematics, the branch of physics that describes motion without considering its causes. Okay, so through this presentation we will learn how motion can be represented graphically and mathematically. The diagram shown here is a velocity time graph. Okay, you can notice that the velocity first increases uniformly and then it decreases uniformly. You can find that here, right? Increasing and then decreasing. Okay. So the upward sloping section represent acceleration. Okay, so this section represent acceleration, and the downward sloping represent the deceleration. Okay, so this part represent the deceleration. Got it. So by understanding the shape of this graph, we can determine important quantities such as acceleration, distance traveled, and final velocity. So our goal today is to connect graphical interpretation with the mathematical equation to develop a complete understanding of motion. Got it. So let's start with the understanding motion through two complementary lenses. Kinematics can be approached in two different but complementary ways. The first is visual language of graphs. Graph allow us to see how motion changes over time, right? For example, distance time graph. It shows how position changes while velocity time graph show changes in velocity. Okay. So the second is the analytical language of equations. The four variables shown here are u. We'll use u for initial velocity, right? So u represent initial velocity. Okay. And what about a? A represent acceleration, right? And V represent final velocity. And T represent time and S represent distance. Okay. So using these variables, we can solve motion problems mathematically. The most effective approach combine both methods. Graph help us visualize the motion and equations help us to calculate exact numerical values. So these are the graphical method and these are the analytical methods. Okay. So now let's see the anatomy of velocity time graph. Okay. So here we can see the most important graph in kinematics, that is the velocity time graph. Okay. Here we have two key features to remember. First thing is gradient. Okay. The gradient acceleration. Okay. So it represent the slope or gradient of the graph. Okay. So they represent the acceleration. So a steeper slope indicate greater acceleration. So how we calculate the slope? Like this, right? So if the slope is steep, okay, a steeper slope indicate greater acceleration. Clear? Mathematically, we can represent acceleration is equal to change in velocity by time, right? By time. Okay. So what is secondly the area under the graph? It represents the distance traveled. Okay, so the area under the graph shows the distance traveled. So area is the distance traveled. Okay, and distance is equal to area under the velocity time graph, as we have mentioned. Therefore, a velocity time graph gives us two pieces of information simultaneously: acceleration from the slope and distance from the area. Got it? Now let's see the shapes. Okay, different line shapes into physical reality. So different graph shape represent different type of motion. So first we have a horizontal line, right, which represent uniform velocity. So since velocity remain constant, acceleration is zero here. Okay, so here the acceleration is zero and distance equal to the rectangle area, right? This area. So here it is 100 meter. Okay, clear? Okay. So here, the next we have a straight line with a positive slope, right? So the slope here is positive, right? So this represents a uniform acceleration. So velocity increases at a constant rate. Okay. So velocity increases steadily. And while we have these kind of graphs, okay, it is a curved graph, right? So it represents non-uniform acceleration. Here acceleration itself changes with the time. Okay. So acceleration changes continuously. Got it? So whenever we observe a graph, we should always ask, is the line horizontal, straight or curved? The answer immediately tells us the nature of the motion. Got it? So this is an important part. We have to be very careful here. Now let's see the distance time graph. Okay. So how to use the distance time graph. So far we have learned about the velocity time graph, right? Here the most important feature of this graph is its gradient. So gradient is equal to change in distance by time. Okay, change in distance by time. Since distance divided by time gives velocity, the gradient of distance time graph represent velocity. Okay, so for example, you can see that the object covers 40 meters in 4 seconds, right? 40 meters in 4 seconds. So the velocity will be 40 by 4, which is 10 meter per second. So notice that the line is straight, meaning the velocity remain constant throughout the motion. Okay. Unlike velocity time graph, the area under distance time graph does not have useful physical meaning. Okay, so both graphs are different. Got it? So now let's see how to capture the instantaneous velocity on a curve. So when a distance time graph is curved, velocity is changing continuously, right? In such cases, we find instantaneous velocity using a tangent. Okay. So a tangent is a straight line that touches the curve at only one point, as shown here. Okay. So how can we do that? What is the procedure? So the procedure is identify the point of interest. Then you have to draw a tangent at the point, and then you have to calculate the slope of the tangent. So first locate, then draw, and then calculate. Okay. So the slope obtained represent the instantaneous velocity at that exact moment. Okay. So this in this example, the slope equals to 20 meters per second. Okay. So we are taking an example that let it be 20 meter per second. So like it will be 40 and 2. Okay. The slope will be 20 meter per second. Okay. This is how you will be calculating. Okay. So that is how we use instantaneous velocity in a curved graph. So here we can see the summary of what they have learned, right? So for a velocity time graph, gradient represent acceleration and area represent the distance traveled. For a distance time graph, gradient represent velocity and area has no physical meaning, right? This is what you have to remember. So you have to always check the y-axis label before calculating gradient or area. Okay. So a common examination mistake is confusing this relationship, right? Therefore, always you have to check the type of graph before calculating gradient or area. Now let's see how to transition from geometry to precision algebra. Okay. Graph help us to visualize motion, but equations allow us to calculate precise values, right? So notice the triangle area under the velocity time graph. Okay, this is the velocity time graph. Check the triangular area. So what is the area of a triangle? That is half into base into height, right? So in a velocity time graph, base correspond to time. Okay, base correspond to time. That is delta t, right? And height correspond to change in velocity. Okay, that is delta v. Okay. So by replacing these graphical quantities with the kinematic variables, we derive mathematical equations of motion. So this process demonstrates how geometry and algebra work together to describe motion. Okay, clear? Now let's see the kinematic lexicon. So before solving problems, we must understand the four fundamental quantities of kinematics. As we have mentioned, U is the initial velocity, right? And V is the final velocity. A is acceleration, T is the time interval, and S is the displacement or distance traveled. Okay. Every equation of motion simply is a relationship between these five variables. When solving a problem, the first step is always identifying which variable are known and which variable must be found. Okay. Now let's see how to identify the correct formula. So students often struggle because they use wrong equation. So the flowchart provides a systematic method. So we have to identify what we are trying to find. If we need final velocity, we have to use this method. And if we need to find distance, the method is different. Okay. So first, identify the unknown quantity, whether it is final velocity or distance. So then determine whether time is known or unknown. So if we know the time, if the time is given, you can use V is equal to U plus AT. If the time is not given, you have to use V square is equal to U square plus 2AS. Okay. And what if you have to find the distance? If you have the final velocity, you can use S is equal to U plus V by 2 into T. And if you don't know the final velocity, you can use S is equal to ut plus half, that is 1 by 2 into at square. Okay. So following this process ensures that the correct formula is chosen every time. So you can take note of this slide. Okay, this will be very helpful for you to identify the kind of equation that you have to use in different kinds of problems. Now let's apply what we have learned. Okay. So let's see the briefing. So a cyclist undergoes motion in three stages: accelerates uniformly from rest, travels at a constant speed, and then decelerate uniformly until it coming to rest. So our objective is to analyze velocity time graph and calculate the distance traveled during each stage. So this example demonstrates how graphs and equations work together in solving real world motion problems. Okay. So this is how it works. Okay. So here the target is to calculate maximum speed, right? And total distance traveled. So a velocity time graph will be provided. Okay. So first you have to find the acceleration. Start from the zero, right? So u is zero. And then accelerate at the 1 meter per second for 20 seconds. So it will be accelerating at 1 meter per second for the first 20 seconds. Then a constant speed for 60 seconds. And then decelerate at -2 meter per second, which means it is the speed is decreasing, right? Until it's stopping at a v is equal to 0. That is the case. Okay. So let's see the solution. Okay. So during the first stage, the cyclists start from rest and accelerate uniformly. So what are the known values? We know u, which is 0. What was the acceleration? Which is equal to 1, right? And what is the time taken? 20 seconds. So what is the maximum speed? You can use the equation v is equal to u plus at. So v is equal to 0 plus a is 1 and t is 20. So v is equal to 20 meter per second, right? That is 72 kilometer per hour. Okay. So now you have to calculate the distance. So you should calculate the area of the triangle, right? So we can use S is equal to ut plus 1 by 2 at square, right? So u is 0 and definitely when 0 multiplied with any value it will be 0 only, right? So here we can take 0 plus 1 by 2 a is 1 and t is 20. So we have to take 20 square here. What is 20 square? That will be 400. And half of 400 will be 200. So the distance will be 200 meter. Okay, clear? So thus the cyclist reached 20 meter per second and covers 200 meters during the acceleration phase. So this is how you have to solve the question. It is very easy to do the problem, so you can try it. Okay. Then we have another case. So during the second stage, the cyclist maintain a constant velocity, right, of 20 meter per second. So this section forms a rectangle on the velocity time graph, right? When the speed is constant, it will form a horizontal line, right? So the distance travel equal to the area of the rectangle. So distance is equal to length into width, right? So here our V is 20 and the T is 60. So the distance will be 20 into 60, that will be 1200 meters, 1200 meters. So since velocity remains constant, acceleration is 0. This stage contributes to the largest distance to the overall journey. Alright, so this is how we do the calculation. And then we have the stage 3, that is deceleration, right? The final stage. So in the final stage, the cyclist shows like a slows down, right? He uniformly slows down until stopping. So what was our initial velocity? Here the initial velocity will change. It is 20. Then final velocity till 0, right? And acceleration will be minus 2. And time is unknown. So you will be using the equation v square is equal to u square plus 2as. By substituting the values, we can find v is equal to 0, which is equal to 20 minus 2t, right? We'll be substituting like this. 0 is equal to 20 square plus 2 into minus 2s, right? So while doing the calculation, that is 400 minus 4s. 4s is equal to 400 and s is equal to 100 meters, right? So you will get distance as 100 meters. Okay. So therefore the cyclist take 10 seconds to stop and covers 100 meters during deceleration. Okay. So now we have analyzed the entire journey, right? Acceleration distance is 200 meter, constant speed distance is 1200 meter, and deceleration distance is 100 meter. So the total distance will be, you can add all, right? 200 plus 1200 plus 100 plus. So it will give you a total of 1500 meters. So this example highlights the power of velocity time graph. Okay. So the slope reveals acceleration and the area reveals distance traveled. So by combining the graphical interpretation with equations of motion, we gain a complete understanding of how objects move. I hope it was helpful for you. Thanks for watching.